welcome to the lesson on standard error of the mean, one of the other statistical things that we need to learn in AP Biology. Before we talk about standard error of the mean, in order to calculate standard error of the mean, you need to know about something called standard deviation. Okay? Standard deviation is a measure of how spread out the numbers are, or how far away they are from the mean in average. Okay? The more spread out the numbers are, and I'm going to give an example of this in a second, okay, the higher the standard deviation is. Okay, this is the formula for standard deviation. Okay, the AP exam does not make you use this formula, but you do need to understand what the standard deviation means, and to understand what the standard deviation means, you have to look at the formula. So what this formula says, okay, is that you have a number, x, and the x bar is the mean. So what this formula wants you to do is take every number in your number set and subtract it from the mean and then square it. Okay? Then you're going to divide that number. So for every single number, you have to take the number, subtract it from the mean, and square it, and then you're going to add all those numbers up. So if you have 50 numbers, you have to take the number, subtract it from the mean, and then square it, and then add those numbers up. Then you take that number and divide it by the number of numbers you have, minus 1, and then after that you square root it. Okay? You will never have to calculate the standard deviation on the AP exam. On the standard deviation, they will give it to you. But you need to know that the standard deviation tells you how spread out the numbers are. So for an example, if we take a look at these two number sets, we'll call this number set A and number set B, okay? The question, okay, is which number set has the larger standard deviation? So if you think about it, if you look at the spread of these numbers here in sample B are much more spread out. They range from 1 to 30, okay, are much more spread out than these that only range like between 5 and 3. So this set here has a higher standard deviation. It turns out, I did the math, it turns out that the standard deviation for this set of numbers is 0.63, and the standard deviation for this set of numbers is 9.93. Okay? But, and again, you will never have to calculate the standard deviation. The point is you know what it means. The higher the standard deviation, the more spread out the numbers, or the more different the numbers for each other. The smaller the standard deviation, okay, the closer the numbers are together. One thing that also is true, if you're doing an experiment, and let's say you repeat the experiment 4 times, okay, you would want your standard deviation of the values that you get, those 4 times, to be low. Because that means your experiment is producing the same results again and again. If you have a high standard deviation in your data, that's not a good thing, because you want to be getting the same results every time. Otherwise, there's errors in your experiment. So when you're doing an experiment and you're doing the same experiment multiple times to see if your experiment is good, you want your standard deviation to be low, because then the numbers that you're getting each time are relatively close to each other. This here is the formula for the standard error of the mean. The standard error of the mean takes the standard deviation, so the SD, which we called, and divides it by the square root of the number of things that you're taking the mean of. Okay? Now that's the formula, okay? Let's talk about what the formula is actually telling you. The formula for standard error of the mean helps you determine how well you actually know the mean of a population. Like, how accurate is your mean population? Okay, and like we said, it takes into account both the standard deviation and the sample size. Okay, couple things. The smaller the sample size, usually the more error you have, or your mean range is bigger. And we'll see this why in a second. Also, okay, the bigger the standard deviation, okay, the higher the standard error of the mean is as well. Okay, because if you have a big variation in your population or whatever you're measuring, that means the error is probably higher. So to have a small standard error of the mean, okay, you want a small standard deviation. Okay, this is to have a small standard error of the mean. You want a small standard deviation and a large sample size. Okay? Calculating the standard error of the mean allows us to answer the question, okay, are the means of two populations or two sets of data different enough to conclude that the differences between them are statistically significant? Okay? And we're going to take a look at this calculation in two populations of monkeys, where we measure their tail length. So, in this, we're looking at the size or the length of monkey tails in two different populations. Okay? We're not going to worry about the median, okay? This was here for another lesson. I moved this lesson up a little bit. So don't worry about the median length. I'm going to talk about that at a different point. Okay? But we have one population where they measured the tails of 81 monkeys, and the mean length was 2.42. And then we have another population, which was they measured the tails of 100 monkeys, and the mean tail length was 2.71. So the question that we're trying to answer is the difference between these two means, is that different enough to conclude that in population A, they actually have longer tails? Like, can we conclude that based on the differences in these means? To do that, the first thing we have to calculate is the standard error of the mean. Okay? The standard error of the mean, like we learned above, okay, is the standard deviation divided by the square root of the number of organisms. Okay? So, for the population A, the standard deviation is 0.51. And then on the bottom, we need to take the square root of the n. The square root of 81 is 9. And then if we do that math, we get the standard error of the mean to be equal to, I wrote it down already, where are you? 0.057. Okay. Now, so the standard error of the mean is 0.057. Okay. Now, we need to calculate the SEM range for plus minus 1 standard error of the mean and plus minus 2 standard errors of the mean. What does that mean? Okay, I'm going to do these calculations on a clean page, but you can do them on here if you have space. So to calculate the mean range for 1 standard error of the mean, you have to take the mean, which was 2.42, and you have to subtract and add to the mean the standard error of the mean. So, we're going to take the mean and both subtract and add the standard error of the mean. When we do that, if I can add correctly, when you add the mean, when you subtract, you get 2.363, and when you add, you get 2.477. So the mean range, the range for the mean, is between these two values. Okay. What that means when you're doing a standard error of the 1 standard error of the mean is that there is a 67% chance, I could write a 6 correctly, 67% chance that the actual mean, okay, is within those two values. Okay, now we need to do the same thing, okay, but this time we're going to multiply the standard error of the mean by 2. So if we take the standard error of the mean, which is 0.057, we're going to multiply it by 2. Which is, if I did this correctly, hopefully, let's see, where are you? It is 0.114. if you multiply the standard error mean by 2. Now you need to do the same thing. You need to subtract the two standard errors of the mean from the mean, and add the two standard errors of the mean. So the mean is still, and we're going to subtract this from it, and we're also going to add it. And when you do this, if you did it correctly, when you subtract, you get 2.306, and when you add, you get 2.534. And that means the range is between 2.306, the minus, and 2.534. So what this means, when you subtract and add two standard errors of the mean, okay, what that means is there is a 95% chance that the actual mean, okay, is between those two values. Okay? Notice that this range here, for the 95% confidence, is much, much larger, okay, than this here. So, what I did here is I wrote in our SEM range for the population A, and I'm not going to show it to you. You should see if you can calculate it and get these answers if you really care whether you can do this or not, and if you're having problems, you can email me. Okay? I did the same calculation that I did over here for population B, and these are the ranges that I got. Okay, now, just to make sure that you know, okay, and this is on the next slide, so you can look at the next slide if you want. I want to leave it on here. If you use a standard error of the mean of 1 and add it and subtract it from the mean, okay, what that means is a 67% chance that the actual mean is within that range. Okay? If you use two standard errors of the mean and add it and subtract it from the mean, that means there's a 95% chance, okay, that the actual mean is between those two values. So generally, in AP Bio, they want you to use two standard errors of the means, because a 95% chance means there's a very, very high likelihood that the actual mean is in there. Now, what's the whole point of this? Remember, the question that we started with is, are these means different enough from each other, okay, to conclude that there's a difference in the monkey tail length in these two populations? If we look at the ranges, and we're going to use the SEM of 2, the question is do those ranges overlap? Okay? To do that, okay, we are going to look at a bar graph of the means. So this is a bar graph of the means. I have population A on the x-axis, and then the bar is the length of the mean, and I have population B, and the bar is the length of the mean. And this I wrote here is the standard error of the mean range for two standard errors of the mean. So if I draw bars that represent these length of this, so the bottom of this is 2.3, that's about here. We don't want to do it in blue. That's about here. And then the upper range is 2.53. That's about 5.3. About here. That's the error bar for that one. And if I do the error bar for this, the low range is about 5.5, which is here. And the error bar goes off this graph. I guess it would be about here. Mr. was lame and didn't make the graph, but I would look here if the values continued. Now notice, if we draw a line between this bar and this bar, and I can make it straight, okay, those error bars do not overlap. Okay. What that means is, since the error bars do not overlap, the difference in the means is statistically significant with 95% confidence because we use two standard errors of the mean. If the error bars did overlap, that would mean that the difference in the means is not significant and that there's no difference between the populations. For homework, you're going to do the same thing with this set of data in this problem that I made up about Ruby and her meowing. Okay, so if you take a look at the data, there's a graph paper attached. Here's the data. You need to calculate I gave you the mean and the standard deviation of the data, and you can count the number of meows by counting. Okay, you need to calculate the SEM, then tell me if the difference is significant with 95% confidence, and draw a bar graph on the graph attached with error bars. So essentially, you're doing the same calculations that I did. If you have questions, please email me.